Okay, welcome back, and I hope you've had a chance to read the paper that we assigned. There's a lot of technical jargon in this paper, and I don't want it to scare you if you're not accustomed to genetics. So I'm really going to just highlight a few points that I want you to focus on, which are really essentially the way in which we're using these specialist genetic techniques, but we're using them in a way that as epidemiologists we're very accustomed to using them in a case control study or a series of case control studies. And then I want to highlight a few wrinkles, if you will, that are a little bit different from the techniques that you're accustomed to if you're just thinking about one study at a time. So actually the first thing to notice about genetic epidemiology is inherent in the list of authors here for this paper. Genetic epidemiology has turned into very much a team science. We've discovered that to robustly identify variation in the genome, it's very important to have a large number of studies, maximize the sample size, and so that means we wind up collaborating with a lot of colleagues around the world. And so the name of the game here in many ways has been to form consortia to do collaborative studies to maximize sample size. So this is a paper where we co-discovered for the first time a specific variant that is associated with breast cancer. It's called sporadic breast cancer here in the title. And that indicates that we didn't study this in families in which breast cancer was very common. That's usually called familial breast cancer. We studied this in regular case control format in series of women who were unfortunate enough to be diagnosed with breast cancer, but without focusing on the women who had a specific family history. So again, this is the fairly conventional epidemiologic study design, a series of cases and appropriate controls. The initial stage that we discussed earlier is the genome-wide stage, where we apply tools that can test many hundreds of thousands of variants in the genome across as many cases and controls as we can. In this case, about 1,100 cases and a similar number of controls. And then we display the data and we skim off the most extreme associations. So I showed you the Manhattan plot in the last example. At the time we did this, I think the Manhattan plot hadn't been invented or is just being invented. So this is the rainfall plot, but it's exactly the same principle, except here, the smaller the p-value, the lower down the y-axis it appears. And each chromosome is represented, and we've just represented the p-values that are less than 10 to the minus 2 or 0.01. And so the further down the dot appears, the more extreme the p-value. So there were extreme p-values here on chromosome 4, chromosome 7, chromosome 10. This one immediately attracted interest because they appeared to be in a gene called fibroblast growth factor receptor 2. And any of you who are interested in oncology will know that anything that's called a growth factor receptor immediately attracts interest if you're interested in a causation of cancer. So we were able to take initially in the replication phase only a very small number of these variants, 6 in fact, but representing the chromosome 10, 4, and 7 initial hits, called hits in the business. But these are all variants. You can ignore these RS numbers. That's just the code that each variant in the genome is given. But you can see from the length of the code that there's a lot of variants in the databases. Here's a chi-square. Here's a p-value. As you can see, there's an impressive number of zeros in front of the digits here. An odds ratio for heterozygotes, so the odds ratio for people who've inherited one copy of the variant allele. An odds ratio for homozygotes, so people who've inherited 2 copies of the variant allele. And sometimes these variants come in the neighborhood of a gene. So I mentioned FGFR2. Here are other gene names, and this gives us a clue perhaps, but only a very preliminary clue to whether this is something that we should be more interested in. So these were tested in a much larger number of cases and controls. So this is table 2 from the paper. The total is about almost 3,000 cases, over 3,000 controls. But now from 4 different studies, each of which were independent nested case control designs. So the nested case control design you talked about earlier in the context of biomarkers. It's a little different from a regular population-based case control design in that we actually do a case control study in the context of a much larger number of people who are enrolled and enumerated in a cohort study. And in very brief, we wait for cases to occur in the prospective study, so those are the series of cases, and then we sample from the non-cases the controls. And there's a few different ways of doing that, but essentially the principle is the same as any case control study, except the difference is we have a full list or full census of the people in the population that gave rise to the cases. Those are the initial members of the cohort study. So it turned out that of those 6 variants, 5 of them didn't replicate. 5 of them showed no evidence for association in this replication phase. And that's very typical of these large-scale studies where we go in without any specific hypothesis for specific variants. We screen at the first stage agnostically, looking at every variant in the genome. Some of these rise to the top of the Manhattan plot and have the most extreme p-values. Now we take them into a replication phase, and lo and behold, most of them drop out. They were just chance associations. They were just false positives. But if we're lucky, some of them will hang in there. And you can see in each study, except one, the association with carrying 2 copies of the variant at the particular site here in FGFR2 was somewhere between a 1.8 and 2-fold increase in risk. One study was positive, 1.22, a 22% elevation in risk. But note that the p-value in that study is not close to the 0.05 level. And so we might say normally, well, 3 of these studies are positive, and 1 of them is not positive. The key is, when we get multiple studies, is to use a technique called meta-analysis, in which we can summarize across studies what the summary information is that all of the studies give us at one time, and generate a summary estimate or summary odds ratio and confidence interval and a summary p-value. And when we do that, the odds ratio is about 1.64 here for the women who carry 2 copies of the variant allele. Not a huge association in risk by any means, but highly, highly significant. 1.1 times 10 to the minus 10, so 1.1 with 9 zeros in front of it. And one of the questions I'm going to ask you is, why do we insist on such small p-values in these genome-wide association studies? But this actually fulfills the criteria for what we think of as genome-wide significance. It fulfills the criteria for a positive association, accounting for the fact that we've tested at hundreds of thousands of points across the genome. So that's the epidemiologic piece of the paper. Again, unless you're particularly interested in genetics or you already come with a background in genetics, just try and focus in on those couple of tables in the paper. And then let's now go to questions for discussion. 5 questions. Why do we insist on very, very small p-values in genome-wide association studies? As you've learned in the context of the rest of the course, most of the time we'll accept a p-value of 5 times 10 to the minus 2 or 0.05 or less in order to declare statistical significance in a specific study. And here I'm saying that we need very, very small p-values of the order of 10 to the minus 8 in this case it was less than that, 10 to the minus 10, before we declare success, if you will, and say we have a finding here that we think is robust and will replicate. So why is that in the context of genome-wide association studies? Why do we need very large samples for these genome-wide association studies? Some of the examples that you've studied so far have a few hundred cases, a few hundred controls, a result that was compelling and impressive and credible. Here, I'm saying that we need thousands of cases, and this was one of the very first genome-wide association studies. It was one of the first genome-wide association studies for breast cancer. In the subsequent 5 years, we've gone on to do many, many much larger studies, and now the largest study has more than 50,000 cases of breast cancer, 50,000 controls. Why have we moved into this very, very large sample size domain when it comes to these genetic results? Let me ask you a question that would apply to any association study or case control study. Association study is the jargon that the genetic epidemiology community uses for what we would consider as observational studies. So association studies are distinct from randomized clinical trials where we're assigning the exposure. Association studies, case control studies, cohort studies, we're not assigning the exposure. It's not an experimental design in that sense. And so we're looking for association, or what is often called correlation in our statistics. Doesn't matter, in this case for a disease like breast cancer, that it's likely that, unfortunately, some of the women who are controls in these studies will go on to develop breast cancer later in their lives. We didn't know that they should potentially have been in the case group when we did the study. Is that a big deal? And the sort of hint here is that breast cancer affects about 1 in 9 women. You might want to think about this question for a very rare disease that affects 1 in 1,000 people, for instance. You might want to think about this question for a trait like high blood pressure, where by the time people are in their 80s and 90s, a very high proportion of the population has developed high blood pressure, is on treatment for high blood pressure. So this is kind of a middle scenario. About 10% of women will develop breast cancer. Think of it for the very rare case. Think of it for the even more common case, or much more common case. One of the studies didn't have a statistically significant result that was independently significant. The result leaned in the same direction, but was not a p-value of less than 0.05. So think a little bit why the results observed in the first study mightn't replicate in any study, or mightn't replicate in all of the studies in the replication phase. What are the reasons behind failure to replicate, or inconsistency in replication? And finally, we had 4 studies there. 3 were clearly statistically significant at the 0.05 level, so I could say 3 out of 4 studies were significant. Maybe that sounds impressive, but 1 wasn't. So why might a meta-analysis, where we get a statistical summary of the best estimate across studies, across all the data of the findings, why may that be superior to the other way of counting up studies, which is to say, I've got a large number of studies of the same thing here, this number were positive, this number were not positive, and this leads me to believe that the association is real or not. What do we get out of a meta-analysis where we get a single summary point estimate that we don't get out of that counting positive and null studies? So those are the questions for discussion. Good luck with the discussion boards, and I'll look forward to seeing you on the discussion boards and maybe returning to explain a few of the nuances here if time permits. Thank you.